All right, let's look at some stuff from 6.2. So, right, chapter 6 is about relations, and 6.2 gives us some properties that relations can have, right? So, reflexive, irreflexive, symmetric, antisymmetric, and transitive. And what we'll see is that, well, I mean, in the next section, in 6.3, we'll talk about a specific type of relation. It's called an equivalence relation. And we'll see how these things play into defining those, right? But here we get a nice definition of what it means to be reflexive, right? And an exercise at the end of this chapter says, find logical negations for the formal properties defining each of the five, right? So if I look at, say, reflexive, now notice what it means to be reflexive is not, right? The irreflexive is not a negation of the reflexive property, right? If something is irreflexive, it also means something specific. Notice in both of the cases, right? These are universally quantified statements. And if I have this negation, I mean, I think this actually comes in earlier, right? But if I have a negation, right, for all A and S, let's see, ARA, right? A is related to itself, right? That's what it means to have the reflexive property. Well, to not have the reflexive property, notice that means that there exists some A in S, right? We could say such that, right, A is not related to itself. Right? Because remember, when we do negation, we do a negation of a universal statement, we have an existential statement, right? And then we'll just negate the A is related to itself. So all they're saying is that there is some A in S such that A is not related to itself. If we had, say, 50 elements of S, right, and 49 of them have the property that they're related to themselves, but one of them does not have that property, then in fact we've found something that exists there, right? And so once again, right, this is sort of our reflexivity, right? We could have irreflexive, right, and we could negate that. Once again, notice that this is a universally quantified statement. So for all A and S, right, A is not related to itself, right? One thing you could think about is that if I defined a relation that was irreflexive on, say, the real numbers, right? If you imagine, like, what does the set or the subset of the Cartesian product, right? So let me look at this, right? So I can define R cross R, and if you don't know, R cross R is just the Cartesian plane, right? And this might be nice for like illustrative, oh goodness, illustration purposes. Imagine this exactly goes through. This is the line, right? We could imagine y is equal to x or something like that. Well, this relation that I've made, y equal x, this is like this relation here, right, or this thing this defined by this line, right? This is reflexive, right? Because everything on the line is right, is related to itself. Yeah. So notice if I were defining, I were defining a subset where, I've got like some point here, and I've got another point down here, and I've got another point here. I avoid points on the line, right? So if I make this relation here, notice that this relation, I mean, it may have other properties, but the relation that I've done here is irreflexive, right? Because I've avoided that line. Right, so there's just a little thing. So let's actually do the negation of irreflexive, right? Right, notice if I had all of these dots and then I put one dot on the line here, right? Notice now it's not irreflexive. It's not reflexive either, right? So in this case, since this is a universal statement, I'll have another existential statement after the negation. There exists some A in S, right, such that A right. Okay. Now, notice, I mean, something here. This is an existential statement. So I guess if you think about it, it doesn't negate, well, by negating that universal statement, I don't guarantee myself that it is a reflexive relation, but it certainly is possible, right? That it's reflexive. It doesn't like say that's not possible by just being existential. It's just that it's not universally quantified, right? Okay, so let's look at some of the other things we have here. Now here I have symmetric, antisymmetric, and transitive. So let's just look at what symmetric is, right? Let's kind of pull this one out, right? For all A and B and S, if A is related to B, then B is related to A. Okay, so I could say something like for all A and B and S, right? A R B, then B R A, right? This is reflexive. So this, some things have this property. And what would it mean for us to actually negate this, right? Well, remember, once again, if I have a universally quantified statement and I'm negating it, I'm saying there exists A and B and S, right? Such that when we want to write, well, remember when I have a thing like if P then Q, right? I can think about that as not P, right, or Q. So when I go to negate this, right, what I'll get is P and not Q, right? So the negation, it's not really good, but anyway, right, the negation of this is P and not Q, right? Using De Morgan's law, we'll just distribute that through there. So I get that A is related to B, and, right, B is not related to A. Right? A relation R on the set S is antisymmetric if, and only if, right, for all A and B, right? If A is related to B and B related to A, then A is equal to B, right? So notice for the symmetric relation, right, there are what it says, no one-way streets, right? And here it says only one-way streets, right? These are sort of like little things that we can think about. So let's see. We have this statement. Right. We've got A related to B and B related to A, then A equal B. Right. So once again, if we do the negation of this, right, if we negate it, you know, what we're going to get is the existential quantifier at the beginning. We're saying there exists some A and B in S, right, such that this is going to be the same, right? This whole thing, right, I'm imagining is sort of my, like, P, right? This thing over here I'm imagining is like my Q, right? So remember, it's P and not Q when we're negating these. So what it means is that A is related to B, and, right, B is related to A, right, but A is not equal to B. A and B are not equal. Okay? And finally, let's look at the transitive property. And hopefully you can see where this is going to go, right? I'm going to have, since I have a universally quantified statement, I better have an existential statement, right? And since I have the conditional over here, I better have an and statement where it's P and not Q, right? So let's look at it. Let's pull out here. For all, right, A, B, and C in S, right, we could say A, oh, that's not what I want. Let's go back. A, B, and, right, we'll say B is related to C. Right, then we could say that A is related to C. Right. And I mean, if you want to think about this, I mean, the equal sign is a relation that has the transitive property less than or equal to, greater than equal to, right? Those signs all have, you know, they all have the property. The subset, you know, that's also an operation that has this property of transitivity. Many things we look at or we take for granted have the transitive property, and so, you know, if one is equal to another, and then that thing is equal to something else, right? We will say that they're equal to each other. But, you know, we can't take that for granted always. Sometimes maybe that doesn't exist, so. But let's look at the negation of this. Once again, if I negate it, right, I'm going to get an existential statement. So we're saying there exists elements A, B, and C in S, right, such that, well, that A is related to B and B is related to C, right? But, right, A is not related to C is basically what's going to happen here, right? So I'll put this in parentheses just to say that way, right? I'm going to say A is not related to C, right? So there we go. Right?